All right, today I'm going to show you how to calculate the electric field of a finite line charge. Now, I've chosen to look into this problem and teach you guys this stuff because I'm personally an aerospace engineer, and on a daily basis, I use something known as a radar range equation, which has a very similar form to a lot of different equations you're going to find in electrodynamics, and in this case, electrostatics. That form is an equation of the form 1 over r squared. In other words, as you travel further and further and further away from your source, the quantity you're measuring, in my case, the power of some kind of radar signal, it's going to drop off as a function of 1 over r squared. So we find this a lot in electrodynamics, electrostatics, and I thought it would be interesting to dive a bit more into these topics and teach you guys a bit about electrostatics. Now, the problem we're going to take a look at for calculating this electric field is stated as follows. We want to find the electric field E, a distance y above the midpoint of a straight line segment of length L, which carries a uniform line charge, lambda. Now, I've depicted this problem as follows at the bottom left over here. So as the problem states, we have a finite length of charge. You want to think of maybe like a wire that's holding charge of a length L, and I've chosen to put the origin at the center right here such that we go out to L over 2 and negative L over 2. The reason why will become apparent as we start diving into the mathematics and the physics for this problem. Now, the problem states that it carries a uniform line charge, lambda. So if the charge distribution is uniform, we can define lambda as the total charge that's encompassed on this line and divide by the entire length. That's what we're going to define our lambda as. Now, the first thing you probably think of in solving any kind of electrostatics or electrodynamics problem is, intuitively, I want to go into Gauss's law. Gauss's law is very simple. It's very straightforward, but there are conditions that have to hold in order to use this. So I know that some students are going to naturally gravitate to Gauss's law, and they may try it. If you do, you would get the wrong result for this particular problem. I want to explain why, because that's going to divulge a lot of important elements of this problem that we're going to use to solve it. So what I'm going to say is that naturally, we want to use Gauss's law. Okay, and the main point here is Gauss's law. So what was Gauss's law? What exactly does that state? Well, Gauss's law it's sort of intuitive when you actually understand the mathematics behind it. But mathematically, what it states is that the surface integral of your electric field E is proportional to the charge that is enclosed by some kind of area, some kind of surface, over epsilon naught. Okay, so what this is saying is that any kind of electric field you have that's flowing outside of some area, right, that has to be equal, has to be proportional to the charge that's enclosed by that actual area. So if we actually tried to use this in this particular problem, we would have to form some kind of area around this wire. So the natural area to use is that of a cylinder. So I'm going to draw a cylinder right here, right there. It's going to go some kind of length. All right, and then we're going to close it. All right, and what you would need, what this is stating is that the electric field flowing out dotted into the normal of that area is equal to the charge enclosed, or it's proportional to it. So if we come over here, get a different color, and we say, hey, look here, we can have an electric field that's being produced by all this stuff over here. Maybe we have some kind of electric field like that over here. But as we go over here, we're going to have a different electric field, right? Because the electric field has more charge over here than it does over here. So we're going to have some X component, some Y component. And what you find is that this guy, this electric field, is not the same as this electric field. And because of that, right, when you dot it into the normal, we're going to have a normal that's coming off straight like that. We'll call this n hat, some kind of normal. And I should write in my electric field, right like that. Right? These guys are not equivalent. So when you actually try to solve this integral, it becomes very, very difficult, right? Because you have to find the E right here, the E right there, all across that line segment. So you could technically use Gauss's law, but it's very inefficient. Analytically, it's probably not the best choice to make. But what you could do, if your electric field was the same all across the cylinder, and I'm going to erase what I put in here. If it was the same all across this cylinder, you could actually employ Gauss's law. And that would happen in a very special case, the case of an infinite line charge. So if this length L, if L approached infinity and extended all the way out, you could actually use Gauss's law. So let's do that really fast, because that result will help us confirm the result we get from looking at a finite line charge. Now, the reason why you can use this for an infinite line charge is the fact that if you have an infinite amount of distance on the left and the right of, let's say, some electric field E, what you know by symmetry is that the electric field that's being produced from some kind of line element, charge element that's flying over here, the X component is going to be the same as the same charge component on the right, so they're going to cancel out. So you only have a Y component, and furthermore, the electric field here, compared to maybe the electric field here, they're going to be equivalent. Basically, the magnitudes are going to be the same. So all along this cylinder, E is a constant because you're going to have the same amount of charge on the left as you do on the right. So the contribution at any location along this cylinder is going to be the same. Okay? So in essence, what you're doing is something special happens for this guy right here, as we're going to find. That becomes special because if it's now constant, and furthermore, our normal vector n, E dot n, or I guess I'll write it out for you guys. So this becomes basically E, the magnitude, times n, the magnitude of that, times cosine theta, between those vectors, basically the angle between these guys. And then we have dA here. And I'll write out the rest of this equation. We still have our Q enclosed over epsilon naught, our proportionality constant. Basically what we find is that, well, this guy, this is 1 because the magnitude of a unit vector is always 1. But this guy is 0, so cosine 0 just gives us 1. And what we end up with is we can pull this guy out because it just becomes a constant. It's always the same just because there's an infinite amount of length on both sides of the location that we're actually looking at. So what happens is this guy pops out, and I guess we don't even have the integral anymore. So we just have this guy times the area. In this case, is the area of a cylinder on these edges right there. So that is just 2 pi times the radius of this guy. And we would have to extend this out to the point we're interested in, at point P of Y. I'm going to call it R in this case. So R is synonymous with Y and the length of your cylinder. So that is equal to the charge that's enclosed inside this cylinder. We know that that is just, well, we can take this, lambda L equals Q, and we end up with lambda L over epsilon naught. So all we need to do is we can come up here, get our red pen, we can cancel this guy off, cancel that guy off, and what we end up with is that the electric charge is equal to lambda over 2 pi epsilon naught r. All right, so we get that guy, and that is a good result. So we're going to box that in with our galaxy color. And that's the result we get. Now, this is for an infinite line charge, and you can see the beauty of Gauss's law, because Gauss's law, when things are nice and symmetric, your electric field pops out, as shown here. You calculate your area, and then you divide it over here. So it's a very simple, straightforward problem. All right. Now, what we're going to find when we start looking at the finite line charge is that it's not as simple. It's not as nice and elegant. So if we take this guy, we're going to save this over here because it's going to help us in the future after we get a result to validate that it is actually correct. And it'll be sort of a check. Because as I say, you want to check your physics. You want to double check. You want to be certain, okay? You want to have ways of actually being certain. So I'm going to erase these results. Give us some board space. And then we're going to jump into the actual problem. And I'm going to explain why this problem is much more difficult. So if we delete that. Now, finite line charge. I guess I'll get rid of this stuff too. So what we know from Coulomb's law is that the electric field of basically just a particle, if you will, is 1 over 4 pi epsilon naught r squared. And this guy is the charge that is enclosed. All right, so that's Coulomb's law. And what we can do to solve this, since we can't use Gauss's law, which is our natural intuition, the choice we'd normally go with, what we can do is we can say, hey, this line charge is composed of little small charges we're going to call dq. All right, so this guy is dq, this highlighted element. And we can define that charge as lambda dx. Now, if we're trying to find the electric charge or the electric field on this point P, we know that this guy is going to impart an electric field that goes whoop, just like that. Okay? We're going to call this E. So it has a partial contribution, we'll call dE, to that point. So, in essence, we can take this guy, what we established previously with Coulomb's law, and we can state that, well, if we have this differential, we can integrate, we can add up all these guys, and that's the key word, add up, sum up these little dq's, and collect these dEs on this point P. So basically, we're trying to figure out the contribution of each charge along this line to the electric field at this point P. Okay? So when we do that, we can get something like the following. We find dE, and that is an ugly E. I apologize. I'm still getting used to this pad. But that is equal to 1 over 4 pi epsilon naught. And then we have the integral of 1 over r, the vector, squared, r hat in the direction of r hat. And then we have dq, okay? So we're adding up all these guys. This guy can just become lambda dx. And this r is the distance from dq to our point of interest here, okay? Now, an aside. Let's recall unit vectors, okay? We know that r hat is no different than vector r over the magnitude, right? So in order to really get the true form of this equation, we have to use this. Basically, all this is saying is that if we have a vector r, divide by its length, so its length is equal to 1, that's a unit vector, remember? Then we just have the direction. That's giving us our direction, right? A vector has direction and magnitude. So if we get this, our electric field of the finite line charge is no different than 1 over 4 pi epsilon naught times the integral of lambda. So I'm making this substitution right here for dq. Lambda over the magnitude of r cubed times r dx. And to back up a bit, all I did over here was I just added in lambda dx. Same thing. All right, so this is our general equation that we're trying to use. And compared to Gauss's law, when the electric field is constant, you look at this and you're like, whoa, that is very complex. How the hell am I going to solve this? How the hell am I going to solve this? Well, usually what happens is this r component gives you an x, a y, and a z component if you're in 3 dimensions. We're in 2 dimensions here. So you have to break this down into multiple components that you're going to solve, okay? So we know that our r vector is going to have an x component in the x direction and a y component in the y direction, all right? So we're going to have an x component of the electric field, a y component, and the total electric field is going to be both of those guys added together. As you can imagine, that's a lot of work, okay? So what you want to do is you want to try and find simplifications of the problem to make your life easier and simplify it down to something that is not as complex, to something that's more straightforward, okay? So in order to do that, what you can do is you can make reasoning as the following. You can reason as follows. Let's say you take this guy, this dq, this charge on the line charge, and we're going to say, hey, I'm going to take a look at the same charge, maybe right here. Same distance, but in the opposite direction. And we know that that's going to provide an electric field that goes something like that. Right? So what you can reason is that it's going to have a y component, but in the x direction, it's going to be equal to, because r is the same, it's equivalent to this r, it's going to have the same magnitude, but it's going to be in the opposite direction. So by symmetry, and this is why I placed the origin right at the center, by symmetry, you could reason that the x components are going to cancel. Okay, the x components are going to cancel. And that would give you good results, right? So then you'd only have to consider the y component. But I know some people are out there thinking, well, wait a second, that's sort of hand wavy. I want to actually see the math. I want to see what's going on. So I'll actually solve that for you guys and show you that there is symmetry here. But you should get in the habit of trying to reason through this and using real physics before you dive into the math to figure out what kind of symmetry is at play here and what terms can cancel out. So this guy right here, I'm just going to move this up, make some room for this. We're going to move that up right there. And this pad is really nice. It's so much easier to work with compared to the whiteboard that I've been using previously at the Kaizen effect. But anyway, we're going to consider the x component. So EX. And what this means is that we get the following that we have to evaluate. So we get 1 over 4 pi epsilon naught. We're going to get an integral. We're going to get lambda On the bottom, we need the magnitude of this radius. Well, this guy is going to be out a distance x. It's going to have a distance y. So if we want the r component, well, that's just the square root of x squared plus y squared, right? Pythagorean theorem, baby. So what we end up with is, I'm going to use parentheses, x squared plus y squared. And all that is going to be to the 3/2. And then we need to take care of this r component. So what we're going to end up with is an x. And we have to integrate over this entire line. Now, through symmetry, you could reason, I'll do it the hard way, you could reason that since this component gives the same e as this side, you could just go from 0 to L over 2 and multiply everything by 2. That would be the smart way to do it. But to show you guys that if we integrate across this whole thing, we get the result, I'm going to go from negative L over 2 to L over 2. So you look at this and you're like, well, wait a second, this looks even harder. How the hell am I going to solve this? Well, we don't have vectors at play here, but it's not the most easy integral you've ever seen. Luckily, the x component is actually the easy part. The y component is going to be much harder, which I'll show you shortly. But what we're going to find here is that we can use a u substitution. So we're going to let you remember that from Calc 2, Calc 1? Good old u subs. We're going to let u equal to x squared plus y squared. And just do what we do with u subs. So we know that we just take the derivative on both sides, du dx. That is equal to 2x. The y is a constant in this case. We're stuck at y right here. And we want to isolate an x dx because that's what we have. That's what we have. Oh, crap. Sorry about that, guys. Still getting used to this pad, but we have this right here. We want to find that so we can substitute that in. So we multiply by 1/2 on both sides. Multiply dx on both sides. And we get the following. All right, so we can take this guy, substitute that in, and that will allow us to finally solve this nasty integral. And I hope my face is not blocking this. If it is, I apologize for that. But what we could do is simply say this is 1 over 4 pi epsilon naught. And mathematicians would freak out when I do this, but I find it's easier to do this. I don't want to convert these limits to the u space, basically our transformation over here, because I'll just transform it back when I'm done. We get the same result, but if you want, you could transform u. It's really not nice. You really don't want to do that. So I'm just going to leave the limits of integration as nothing. And I'm going to pull out the lambda right here. And then x dx becomes 1/2. And you get the du. And then we have a u to the negative 3/2. All right? So when we get this, what we end up with is, we can evaluate this pretty easily, right? So we get a lambda over 8 pi epsilon naught. So we get a u to the negative 1/2. And then we get a negative 2 out front, right? Just simple integration that all you guys have done previously. And what I'm going to do is I'm going to make some board space over here. And this guy is a box, so I'll have to get rid of that. And then what we could do is we could just take this guy right up here. So next, what we want to do is convert back to the x space. Go over there. And we know this is just equal to lambda. Negative lambda. The 2 over 8 becomes a 1 over 4. And then we just have 1 over square root, our u term, which is x squared plus y squared. And now we can finally use our limits of integration. So this goes from negative L over 2 to L over 2. And as you can see it's going to cancel out to 0. So our intuition is good here. But I'll work it out for you guys. So we get a negative lambda over 4 pi epsilon naught. And we're going to get 1 over square root of L over 2, this whole thing squared plus y squared. And then we're going to subtract the same thing. The thing that saves us is this square term right there. So we get a L over 2 quantity squared plus y squared. And we find that EX is equal to 0. That's an awesome result. So that tells us that our intuition about symmetry is spot on. The fact that if you take any charge over here, it's going to have a charge that's the same distance in the opposite direction, which is going to impart an equivalent electric field in the x direction, which is going to be in the opposite direction as this dq. It's going to cancel it out, and you're going to get 0. As you work through these problems, you're going to build up that intuition. You'll be able to spot these simplifications. You'll be able to take advantage of it, and it's going to greatly simplify your life, okay? It's going to greatly simplify your life. So we found that the x component is 0. That's great. Now we want to be concerned about our y component. So as I make some board space over here, we got the y component. So basically we just get the same thing, but we have a y in there. So we find, if I grab the right pen, EY is equal to 1 over 4 pi epsilon naught, and we're going to have to integrate still, lambda y over x squared plus y squared, again, to the 3/2 dx. And again, I'm not going to use symmetry. I'm going to do it the good old-fashioned way for you guys. It's going to go from negative L over 2 to L over 2. Again, you could go from 0 to L over 2, basically this half, multiply everything by 2. I am not going to take that approach here, okay? So, you look at this integral. We got all the physics is done. Now it's just hardcore math. You look at this and you're like, how the hell do I solve this? How the hell do I solve this? The way in which we solve this is we remember back in the day when we took Calculus 2 and trudged through all those difficult evaluations of integrals. We remember trigonometric substitution. Do you guys remember trigonometric substitution? That's how you actually solve this integral here. And when you see this integral in a lot of textbooks that actually solve this problem for you, they're not going to run through these steps, but I want to run through the steps for you so you know exactly what is going on here, right? I don't like to skip steps. I'm your buddy. I'm your pal on this journey through physics. So we're going to run through all the math, all the dirty math, the nasty math. And I like doing the mathematics. I like the Cartesian interpretation. I'm going to show you could actually evaluate this in a geometric sense, which makes it a bit easier. But I prefer the Cartesian approach, so we're going to go with that first. And the way in which you're going to solve this is, I want you to recall the following. Recall some trigonometric identities. So if you have tangent of theta plus 1, that is equal to the secant squared of theta. And this is the name of the game for a lot of trigonometric substitution. We see we have an x squared plus y squared over here. So if we could have a tan squared plus 1, we could pull the secant squared in, and when we throw everything on the top, do our substitution, you're going to find it's going to cancel out really nicely. So the one I'm going to use is going to be the following. I'm going to say tan theta is equal to x over y. So we could draw a nice triangle out like this. And we could say this guy right here, this is going to be our theta. All right. So tan theta says we got an x right there. We got a y right there. And we're going to leave that there for future reference. Okay. But if we take this, what we need to do is we need to get a d theta so we can plug it in for this dx. And we do that by taking the derivative with respect to x on both sides. So first, we're going to have to use the chain rule. So the derivative of tan is going to be secant squared. Okay, so when we do that, we get secant squared theta times d theta dx. And on the right, the derivative of x is just 1. So we just get a 1 over y. All right. So what we want to do is we want to isolate dx. So we get a secant squared theta d theta equal to 1 over y dx. And that is a nice result. So we are going to highlight that because we can. No. We just want to make note that it's special with our Galaxy ink. All right. So, whoa, how the hell, you look at this substitution and you're like, whoa, wait a second. How the hell am I going to throw this in here? Well, I'm going to show you really fast. In order to do that, what we're going to do, I'm going to pull out the lambda. So we're going to get a lambda over 4 pi epsilon naught. We're going to get our integral. We're going to get y. And we're going to want to pull this y squared out. So if we take y squared and do something like y squared times x over y squared. I don't know why it did that. It's an ugly x, but it gets the job done. It gets the job done. Plus 1. Well, this is basically the same thing. So we're going to take this and y squared to the 3/2 gives you y cubed. So we're going to have a y over y cubed times x over y. I'm sorry, guys. I have objects getting formed for me unintentionally. This term squared plus 1 to the 3/2 dx. And we find this just becomes lambda over 4 pi epsilon naught integral. We're going to have the dx over y secant squared d theta. And then we just have a y squared on the bottom. So we get a y squared tan squared of theta plus 1 to 3/2. And we have our d theta. Now it's important to note that this y is a constant term, right? This is a constant. It's the distance y that the point is located. But what we find is we see this guy and we look at this. Whoa, wait a second. We can pull in a secant squared, and that's going to simplify this integral. Okay, it's going to simplify it drastically. So what we end up with, and I hope I'm not writing over my logo, we're going to have to jump up to the top shortly. I guess I'll write it out and see what happens. So we get a lambda over 4 pi epsilon naught. All right, so I'm finding that when I made this substitution, we had a y already, which cancels out with this. The 1 over y is down here. So we actually only have a y down here, which I have corrected. So going back to the problem at hand, we get a y down there. And we just have our integrals of secant squared over, well, this guy is secant squared. So secant squared to the 3/2, well, that's secant cubed. This is secant squared over secant cubed. So that's just 1 over secant times d theta. And that is a much nicer integral to solve than what we have found. And this actually, which I'm going to show shortly, I'm going to make some board space. We're going to get rid of our Coulomb's law. And what we find is that 1 over secant is actually cosine. So we get this nice integral. We find EY is actually equal to lambda over 4 pi epsilon naught y times the integral in the theta domain of cosine theta d theta. And as I mentioned previously, you can also solve this geometrically. So I prefer to do this Cartesian based and working through all the trigonometric substitution, but you could also come over here and take a look at what's going on and say, whoa, wait a second. If we select a black pen, we know that this distance here is going to be, or rather, if we take this electric field that's produced by this element, we're going to get an electric field, an angle theta. That theta is over here. Well, wait a second. We know that this is x, this is y. Cosine theta just becomes, of this triangle right there, I guess I could draw it in. This guy, like that, of angle theta, cosine is just y over the square root of x squared plus y squared, which is literally the same thing we've been working with here. Remember, we had a y over square root of x squared plus y squared. So you see, there is sort of like a geometric intuition. You could use that. You could say, well, I don't care about the x component. I'm going to use symmetry. The x components cancel. dy is only in the y direction. So across this line charge, each infinitesimal charge is going to contribute to an electric field in the y direction. And you could solve it that way. But we worked through the Cartesian method. This is what we got. We can actually solve this finally, get the result we're looking for. But it is nice to double check. As I say, if you solve something twice, that boosts your confidence drastically in the end result. You want to try and do that when you're working through results that you're deriving, especially for the first time. Well, this is sort of an easy one, but you want to use this to get into the habit of doing that, okay? So as we try and solve this, we get our constants out in front. We get the lambda over 4 pi epsilon naught y. And the integral of cosine is just a sine theta. And then we have to convert back to our Cartesian domain. So that becomes lambda over 4 pi epsilon naught y. And sine theta, we can use this because we said tan theta is x over y. Sine theta is just going to be x over the distance of this guy. So that also looks very similar to this triangle, right? X over that. Same thing. Okay, so we end up with x over the square root of x squared plus y squared. Pythagorean theorem, baby. All right, so we end up with this guy, and now we can actually use our limits of integration. So this is going to go from negative L over 2 to L over 2. And we could actually evaluate this right now. So I'm just going to double check. Yes, I got the right result. And when we actually put this in, the result we get is as follows. We take out our constants. Lambda over 4 pi, epsilon naught, y. So we're going to get an L over 2 over L over 2. That guy squared. That's under the square root plus y squared. And then we have to subtract negative L over 2. Basically the same thing. The square root of L over 2 squared plus y squared. All right. We see these guys cancel out, so we get a plus. And the result we end up with is we get a lambda over 4 pi epsilon naught y. The L over 2's are going to add together, so we get a lambda L times 1 over L over 2 quantity squared plus y squared. And then we take the square root. All right, so this is the end result. The y component, we know the x component is 0, so what we could technically say is that the entire electric field going to be in the j direction at point y is as follows. That's an awesome result. So we are going to use our awesome Galaxy ink because this is the result we derived from the beauty of the universe. All right, so that is our final result. And it looks, I don't know, it looks fine. But what you want to do is you want to take a look at this and see if you can use your intuition to reason whether it's correct or wrong, okay? So I'm going to create some board space here. And then we're going to assess different situations using this result that we've obtained. All right, so you know what? This looks sort of similar to the result we got for an infinite line charge using that beautiful Gauss's law. Can we use this to check our result? Well, what's the difference between the two? That's the question you have to ask. The difference is we took the length L and set it to infinity. So let's consider the case when L goes to infinity or L is much larger than y. So in that case, what's going to happen is something interesting happens under here. Okay? So if L is much greater than y, we know that this entire thing can simplify, right? It's basically like saying, let's say this quantity here is like 1 billion, and this is 0.000000001. If you square that, it gets even smaller. But if you add that to this guy, it's pretty much the same number because it's so big. So what we can do is we can simplify this and say, well, this is pretty much, this is just L over 2 squared under here. And what happens is this equation just becomes the following. So we just get a lambda L over 4 pi epsilon naught y times 1 over L over 2 squared, square root of that, which is basically L over 2. So you can flip this guy up there. And what you're going to want to do is cancel these guys. And you get a result. Lambda, the 2 cancels with the 4, over 2 pi epsilon naught y. Oh, wait a second. Look at that. These guys are identical. All right, so the fact that this matches up greatly boosts our confidence. If we could do it a second time, that would further enhance our confidence in this result. So we looked at this result that we have right here. Another thing you want to do, and you want to use this check quite often in electrostatics and the problems you derive. I'm going to get rid of this. Next, you want to see what this result looks like if you travel very far away from where this line charge actually is. So the case we want to look at is, we want to consider the case when y, the distance of interest, goes to infinity. In that case, y is much larger than L. So we're going to play a similar game to what we did previously, and we get the following. We know that under here, something special is going to happen, but in this case, y is going to be larger than L. So it's sort of like this is the super large number, and you can ignore this guy right there. So what you end up with is your electric field is lambda times L over 4 pi epsilon naught y times 1. This becomes 1 over the square root of y squared, which is just y. So we get that term there. And what we end up with is lambda L over 4 pi epsilon naught y squared. So this y is sort of like the distance out, the r term. And this should look very familiar to you. We want to put our j hat in there. It would probably simplify to an art hat, but what I want to say is this guy, you can look at this and you can say this is just Q enclosed. And I want you to recall Coulomb's law from the beginning of the lecture. So we had the magnitude of the electric field for Coulomb's law is the charge, or it's not the charge enclosed, it's basically the total charge over 4 pi epsilon naught r squared. Well, if you look at that, lo and behold, these guys are equivalent. We probably got the right result. This guy right up here is probably the right result. So we can feel confident in that. And that, ladies and gentlemen, is the electric field of a finite line charge. I tried a few different things here at the Kaizen effect. I tried having a green screen behind me. Tried having this nice whiteboard up here. More digital graphics as opposed to having a whiteboard, which is actually located behind me right now, behind my green screen. If you like this, let me know. Drop a comment below. Tell me what you liked, what you didn't like. I'm still getting used to this. So I'm going to put out some practice videos trying to get better at this. But in the meantime, make sure you smash that like button, subscribe to the channel, and hit that notification bell so you can get notified of when we get new videos coming out. I'm also contemplating about potentially having you guys submit questions and problems that I can solve either live. Do you want live streams? Do you just want me to solve problems and questions you have? So feel free to send any problem you have that you want me to solve for you for free, yes, free, to ed@thekaizeneffect.com. And I will store that and potentially make videos to solve problems for you when I figure out what exactly I want to do for the next steps for the Kaizen effect. So that's that. I hope you enjoyed the video. Stay tuned for more videos in the future. Thanks for watching.